Hello.
Yes.
Are you going to present us, right?
She's here already. I can see her on the YouTube page.
Hello, everyone. My name is Vita, and Aditola just told me to keep going. So thank you, everyone, for joining us today. And I think Aditola did a great job to organize this event. During all this week, you will be listening not just the teachers of the coding or some cases studying. You actually will be journey people who solve cases by themselves, and they will share the experience. And we will try to do the same with my colleague Elena. So now I'm hearing myself back. Just a second. Yeah. Okay, so thank you again for invitation. It is an honor. I've been following many people, particularly from Nigeria, in the subject of ML and IE, and I was very surprised when Aditola contacted me and asked to share my experience. I hope it will be interesting and useful for you. So I will be speaking today. My talk will be divided on two parts. I will be presenting just kind of overview in the industry, and then I will introduce you our task and why we solve it using ML and techniques. We actually could not use alternative. We were needed to use that. And Elena will go after in her part into details through the code. So first of all, if you could please go to, you probably already know this, menti.com and use this code. It's so many of us in the room. It would be really nice to know what's your experience and what's your favorite subject in Geo. I in particular work in Geo-exploration, and I'm specialized in quantitative interpretation. So if you just go there and answer a few questions, and then you will get a link with overview, and you also will know who is in the room. But I will continue. So I have been working in Press-Tac Solution Gear for the last 10 years, and I think it's quite a unique company because we work on the border between industry and science. We monitor worldwide what kind of solution been developed and try to implement it into production. So today I will be talking about the cases which actually work into production. You can learn a lot academically what exists in the conference and the paper, but I'm interested in what kind of solution I can implement today so it gives me value to de-risk this prospect. Our company mostly doing seismic processing and quantum interpretation, and I in particular work with quantitative interpretation. And here's a quick overview of my talks, about 20 minutes. I would like to entertain you a bit because we're all learning. We're learning all our life in school and university, and then in our career. We work in a very interesting industry. And maybe ITs, they need to learn every single day. We need to learn maybe every second day, but our industry changing rapidly and we need to learn every day. So I would like a bit to have some entertainments for you as well. And then in the second part of my talk, I will introduce our task, what we managed to solve with ML and what's our result. So I would like to give some, it's my vision, my overview of the industry changed within the last 15 years. Today, we're all speaking about energy companies, transition, digitalization. But honestly, I would not call energy company, I would call us oil and gas company. Of course, we are not speaking about the geothermal. And I proud the industry where I'm working in. It's very interesting subjects. It's we're playing computer games every single day. We're playing computer games. And if you today know Geo or any subject in Geo, and especially coding, Python, I will show you just a bit further. Tomorrow you're going to have jobs. So I would say that in about 2015, when we got the crisis and all, we got this buzzword on marketing. It was advertising for digitalization. And I was thinking, what exactly digital? When I joined in industry, everything was digital. What they mean? And then they start this marketing, I would believe people kind of mainstream, the digitalization kind of linked to optimization and actually ML and AI. Okay, and there was a two main conference, one of the main conference, I believe SAG and EG, I attended in 2015. I have not been in Middle East and Asia, but I believe there was the same story. Where you go through the conference floor to every single booth and every company try to say, we have ML, we have AI, and then you come in and say, so what exactly you have? Oh, we have a link to the Python, and you can do within our platform whatever you like. So, okay, you go to next company and say, what do you have? And the story is repeating. So this is just a gap for you where you will be needed in the 2-3 years, definitely. Every single software try to have some kind of link to Python code where you can bring new solution immediately to geo-exploration. So regarding the artificial intelligence techniques and machine learning, we used them before in exploration as well. For example, I put this mark to 1990s where even Charisma had clustering within attributes. Yet it was much more slower, but it still was possibility to analyze big volume of data and have a look at some maybe geo bodies and to predict some similarities. And then to 2015, we already had a lot of PCR analysis, neutral network. We've been using, for example, Hampson-Russell, that's what I'm specializing on, and quantum interpretation. From 2006, I think they already have raw properties prediction of P waves using machine learning algorithms. We always use it in the clustering, but today we do have possibility to have a link within our software and to add additional solutions to add the values. So 2018, I would say it's more new companies appearing and it starts to be more into production, not just some kind of test. We start to use it in the industry, like fault interpretation, pattern recognition, right? And today I did this list that what I already see in oil and gas companies, what they use to de-risk their prospects. And if you're especially new to the industry, I will show you a couple of software which I do not get any benefits. I'm not advertising anything. I'm just showing what I found interesting. It's today into production, and we use it on a daily basis. So I would like to concern two topics. I'm observing in LinkedIn that many people saying, "Oh, you're working in backwards industry. You have to close all," especially here in Scandinavian countries, close all oil and gas industry. You have to go to renewables. But first of all, what is renewables? There is no renewables. All renewables are newables. So we are working in an industry which support modern style of life, and we will need a specialist for tomorrow. We will need you learning geodiscipline and learning Python, because we do go for optimization process of bringing more artificial intelligence subject to optimize. We're working with petabytes, terabytes of the data, and we need to have some kind of optimization to do faster, and you will have a job tomorrow. What I also noticed, I hear some criticism, even when I'm going on the street, I meet some young people from supporting some kind of green technologies, and they're trying to convince me to vote for green, but nobody doesn't want to be not green, right? Look how many solution engineering scientists create today. Offshore industry, chemical, filters. In Norway, we are super green energy. We have so much environmental friendly solution. We even burn our accompanied gas. We're sending to UK and burn it there, so our air is clean. We actually, we are trying to bring to be a green energy, but we need oil and gas, and we will need it tomorrow. So, you know, I was studied from, I had the privilege to study from academics. I studied in Russia, and there's like a bachelor degree, master degree, PhD, then doctorate degree, then I think член core, and then if somebody died out of those genius people, you have a privilege to be academic. So I studied from Dobritsov. He's one of the people who made big input to the tectonic, to geology, to mineralogy. And he told on the lectures, if somebody tell you that oil will be finished in 50 years, spit on their face. Exactly said. From academic, oil will be enough for some 800 years and coal for 1,000 years. We need these materials to support, I will repeat, our modern style of life. So I would like to confirm your decision to choose geo-exploration or geo-discipline, and especially Python today, or learn to code, because you will help us to bring new solutions fast, and you will bring novelties and your own innovations very fast, so we can go and de-risk the prospect. Another topic that I would like to to speak about, it's the, I see it in LinkedIn a lot. It's interviewing in human resource processes. There are brilliant human resource guys, brilliant recruiters who's helping us and guide us through the process. And I see today it was a crisis. And I see it's a lot of people discussing something up to suicidal thoughts, going through the 400 interviews and still can't pass it. So please just remember my words. None of recruiter process is worth your health, nerve stability. If you went to 400 interviews and didn't pass it, organize your own company. I know at least 3 people who is in the high-tech managers within the artificial intelligence department, and they tell, I can't pass these interviews, I can't pass this special mathematical or verbal test, but I know how to solve my task, and I know how to organize or create the task to solve it. So that's why a bit more motivation to you. Don't be frustrated, don't take it personal, any loss on your interviewing process. I again confirm you do right by joining geological disciplines and Python. And also I was noticing on LinkedIn was some comment like, oh, I would not go for petroleum today. Why? Because it's just some crisis. Today it's crisis, tomorrow we'll need our resources. What should you do? Go to banking? Or if I love my rocks, why would I learn some banking, be disappointed all my life through the career? I would like to go and work in the geo discipline. So again, you did it right, great choice, totally supporting. I love my subject. And now I would like to give you just small overview what I mean by you're going to have a job in 2-3 years. I think it will be a lot of job created within the company, like it was created recently. Every company started to have digitalization manager, yeah, the manager who is trying to link digital to ML and IE. So I believe it will be also space for people who knows Geo and knows Python to work within the platform. For example, if you just go to YouTube and Google Petrel Segal, they did a very interesting solution. So within the database what you have in Petrel, you actually can bring your own solution by knowing Python. Or for example, this company, Paradise Software. I noticed them first time when I've been in on the conference in the SCG in States, and I saw that many people, many companies was promoting similar solution, but they've been maybe one of the oldest. So they was working with PCR analysis for like 20 last years, and they also brought down fractures and direct hydrocarbon identification by using artificial intelligence techniques. So if you have not seen them, have a look on them and similar solution. I'm speaking about those products which is into production, which was already working to de-risk our prospect. Or for example, this company, more new, but they did brilliant solution. You can't deny they did a lot of work to condition the data. I would be a bit more concerned here about the seismic process in particular. Look, they do show here noisy data, and then by using artificial intelligence techniques, they're doing so smooth and brilliant for interpretation. Totally agree. Look, to pick horizon to define your horizon for static models, it's really nice. Another question, when you formulate a task and try to solve a particular problem, you have to always put attention if I do not damage my data, because for geological interpretation, it's really nice, but what about extracting rock properties? I will show you a bit later. But again, new company ready for production, brilliant. One more company, love them. Maybe you already been working with them. It's a Rock Dog. They work with rock physics, and already in 2015. And I think I was seeing it even earlier. Look here, ML Python. Again, a gap for you to work tomorrow. You can take a new article and say, oh, this is new solution was very interesting. Let's try to implement it within this platform. This is a job for you tomorrow. So the good choice. Or for example, Geoteric. Probably you saw before. Fault prediction. Yesterday we did it for a very long time. Today it's taking minutes and it's ready for us to analyze data and bring it to the static, for example, models. They also did the geo-body prediction. I believe maybe it's similar to the Paradise doing. Also have a look at them, very interesting solution. And recently I've been seeing this article on LinkedIn. So Steve Cuddy did, it's a very interesting article because he's showing several examples where artificial intelligence technique worked brilliant, very good examples. And then in the end, he gives some kind of overview in general where it could lead us and give some pitfalls. So have a look at that. So, and comment here back to our scale. So here we are today. So you did the right that you joined this event. Please don't afraid interview. I know how painful it could be, but you joined a great industry and very interesting. Look, we are playing computer games. I have at least 2 software in my screens, which I'm using every day. But to supply solution to the client, something interesting, I actually use additional codes. So I'm taking data out, process and bring it back to solution. And we do everything from seismic processing, rock physics, synthetic modeling, compare it to our seismic response. And then my passion is to predict where the oil and gas, where the shale, sandstone, what kind of type of rocks, is there any porosity inside, what kind of fluid within that porosity. This is my passion. And today we will show you example how we managed to predict fluid of oil and gas within the seismic. And I will explain why it's not possible to use it, alternative methods, only machine learning was working there. Before I jump to our task, I would like to put attention, you can code very well, you know, you can learn many different algorithms and quickly manipulate with the techniques, but put attention to your task formulation. Very careful with what you want to solve, and if you're not damaging the data or not damaging solution by solving the task. Now, for example, here, when we work in geo-exploration, our main instrument or the biggest needed instrument for us, it's a seismic. And in a seismic, when a wave reflected from the border of 2 rocks, we have this amplitude. And we can teach our machine by saying, okay, you see, no, maybe not this example, but another. You see, this is type of the noise we want to remove. This is a radon noise, like deep in multiple noise you could see on the gather. You want to remove it. But will you not destroy the true amplitudes? Because for interpretation, that will be enough. But for rock properties extraction, rock physics, and inversion after, we need to have this value as true as possible. So whenever you try to solve something, try to understand, do I formulate my task properly? Will I not damage the data for further investigation? For example, here is a real gathers. Geologists worked on a stacket of this data, did all interpretation properly, stratigraphical interpretation, saw some anomalies, and asked us to run inversion and to predict properties. And I was doubting about the quality of the data and asked, can you give me the gathers? So I don't want to work on Avios stacks. Could you please give me the real gathers? And what I saw, not even regular spaces. It's so many PhD work today done, and even companies trying to promote processing by using artificial intelligence techniques. Again, I would be today, not tomorrow. Tomorrow, maybe everything will be fixed. Today, I would be still doubting. Look, not regular spaces. I'm just doing simple steps for conditioning. Here's the reflector, you see? When we go back and look at this data, you can't see really reflector. Only if you go and do some processing steps, you actually see there is a reflector. So if we learn on the data and trying to process and clean the data, will we catch the real reflector or not? So put attention when you try to process it. And here is another example. Again, this is intercept multiplying gradient. It's in the avio analysis, we perform this computations to see anomalies of the reflector and if they refer to hydrocarbons. Geologically, the stacked data was looking perfectly. We can pick horizon, we know where the well drilled and how the rocks looks like. But if we start to analyze, we could not see any real reflector, real response of the environment. So when we reprocess data, that's the response how it looks like. This is a cloud tower anomaly. This is reservoir, and in 3D it was visible like this. So when we condition, precondition, or looking at the data and looks somewhat very nice, we have to put attention. Does it really represent environment, the seismic refraction, reflections? Will they give us chance to extract through properties properly? So task formulation should be very important, what we try to solve, and then to choose the methods how we want to solve. And before I will go to our task, I would like just to make a small pause. Yeah, are you concerned about increasing intelligence, artificial intelligence? Totally stealing from LinkedIn. Loved it and wanted to leave for you as a joke. Or this one. And if you try to solve something by bringing in new algorithms, have a look if you've done it simple, or it could be done even more simpler, so no complicated tasks. This also totally stolen from LinkedIn. Then, if you have any question for me for overview, so I just wanted to confirm your decision and to say that you did a good job by choosing this discipline. It's very interesting and you will enjoy it, if especially entry level. No question. Can I go to the task then? What we are going to solve today?
Yes. No question. No question on my
No
part.
question from here.
Thank you.
So what we are trying to show you today. Second. It's the video is going a bit with a delay online. Question in the YouTube, you mean, Aditola? Question from the YouTube? I'm a bit lost. It's so many people writing and to follow. Yes. Okay. What is the role of Python in seismic processing? That's what I wanted to put your attention on. With the Python, you know, we are manipulating the petabytes and terabytes of the data. Today, even the task what we brought for you, it will be not in even SIGY format, it will be in CVS format for you to speed up the process. But if it's Python or if it's another language, if you find some kind of interesting solution which can speed up our some of the flow what we do in a person, why not? If you find some optimal solution, it doesn't matter if you use Python or any other language. If you're fluent in Python, please use it. If I answer the question or just to review things. Well, I will be available and further you can write questions and I can answer even on LinkedIn, for example, or even YouTube. I will review it later. Okay, so I would like to introduce our task to save the time, and you can go more for coding on the second part of our presentation. So that's what we are going to present to you. It's originally was initiated by 3 companies. So AGGS, it's the owner of the data. Gamma Geoscience was preparing the logs, and PSSG, we did the processing, we did this, propose the solutions. So it's based on the Innovation Norway grant supported by oil company Lime Petroleum. And we have been presenting it already in DigX conference, some of the data. We presented an EEG to Min in Russia, and through this particular code you will go through. And I heard today it was a bit kind of complained that ML articles are not reproducible, so you will have a chance to reproduce this one. And we submitted to EEG, but since it was delayed, so we don't know if it's accepted or not. We will use the same data, but we will not show exactly our solution there. It will be presented if it's accepted by Elena on a conference, but she will give you some kind of directions what could be done, or maybe you find a better solution. So what we exactly did, we're interested to find where the oil straight away. It's so many subject can be addressed within our geodiscipline, but in the final end, we would like to know where is the oil. So what we tried to do, when the crisis came, oil and gas company didn't spend the time, money at all for exploration. And we were thinking, what if we take old vintage data, merge it in one big cube, and prepare this data to be able, so the quality will be acceptable for extracting rock properties. So it will be ready for inversion. And that's what we did. We did a mega grid, we processed each cube, we did a control over phase. So it's ready for inversion. And then we thought, what if we learned from the wells and recognize from seismic data? Will it be possible to make some kind of quick scanning tool so we know where the oil or where the water, where our reservoirs? And this task will be your first one. You will have 4 wells and this arbitrary lines through reservoirs. And you will see the difference when you have only 4 wells here or only 2 wells here below these horizons. So how to deal with a very little amount of data, what kind of features you can do to actually extract the value of the seismic and find the reservoirs. The second task for you will be, what if we have inverted volumes? For example, here we have only seismic. Since we have stacks, we do not really have any rock properties. By classic solutions, we can have only some attributes. So you will use here 11 attributes. But later on, we patented solution to estimate density and velocity out of stacks, out of stacked data. And you will get this density, velocity, impedance, porosity, and volume of clay, these 3. And this is the vintage data of merged seismic. And you will see the difference. What if we only use seismic data? Or what if we use properties, more valuable data for recognition? And here you will have 7 wells, and one well will be a test well. And here is a 2D line going through this well, which will be not participating in any learning process. And you will try to predict reservoir. And the third task will be, you will get 3D within one formation, within the same wells, and you will try to predict reservoirs. So the final look, it should be, no, I will show a bit later. The that's the data available. You will have logs. This is the target parameter. So VP, density, target parameter, saturation. We will simply solve this task for 0, it's a water, and 1, it's a oil, just 2 parameters. We have volume of clay. We work in a region where the sandstone with the reservoir. And what we found interesting is we were learning from synthetic trace. If we learn on a seismic data, it can have noise which can distract us from the true. So we decided that we will generate synthetic trace and learn from the synthetic and plus the logs, and then recognize it on the data. That was a feature which was actually acknowledged by many different specialists, saying that that was an interesting solution, because even those solutions which we have before, they was recognizing on the seismic data. There was learning from the seismic data or from the attributes. That's one of the interesting things which we've done. And here's just the overview of how we work. Logs, different type of the logs, target parameter, and then we create synthetic data, attributes as our training set. What also as a feature I would like to mention, sandstone in the North Sea and sandstone in Australia, we geologically will keep call it sandstone. But mathematically, if you go by numbers, it's totally different parameters. That sandstone which we define in North Sea can be carbonate in Australia. So I would not learn in a Norwegian Sea and go to North Sea to recognize, but I would go between the wells to recognize between the wells. This is something for you to consider, to think for the future. These questions in the recommendation articles, yes, we can specify it a bit later. Yes, sure. So then this is our training set, and then we go on our recognition set. So first we go to the seismic and attributes, and if you have any inverted volumes, you can, for example, do P impedance. Yeah, this is our recognition set, and we try to predict the target parameters. That's what you are going to try to do today. So you will learn on the wells. It's just an example, so I'm saving time for you to code by introducing this task. And Elena will tell you what was the difficulties when we have so little amount of data and how to address it. And this is finally what you should get, or do it better. And I would like to say this is outline of the gas reservoir, but actually it's much more thinner here. So our prediction was really well. And it's computing for some minutes, seconds. So it's very, very interesting, very useful. And it's today already ready into production. So what's time for me? Yeah, still have time. So we presented in the DGEX some case when we use this wells in yellow colors from the south, and we went to the north and would like to recognize from the available volumes and predict hydrocarbons. This was the result by different algorithms. And what was interesting that when we look at this particular corner, I zoom it, we predict so much oil, but outlined was only here and there by drill proved, and this was as a dry well. You start to say, what exactly we did wrong, or we re-evaluate the wells. And then we noticed then one well has a missed reservoir, it's missed pay, and another well has shows all the way within this formation. And we even noticed that it was the records at the rig that there is a hydrocarbons there. So by these techniques, we will not be able to predict its production reservoir, its commercial volume there or not. We only will be able to say if there is oil or water. There's indicators of the hydrocarbons. So, and here is our work where we apply in production this work. This is the outline of our merge, in particular slice from sandstone volume. And we learning on 157 wells, so every second well, and every other second well, we are testing if our predictions are correct. But this will be already, these models, they will be commercially, of course, available for oil company and within this Innovation Norway project. But those codes which you got today from Elena as well, they will be also published on GitHub. Yeah, Elena, yeah, it will be available. So you can see through. And what we also wanted to do that for your future if interviews or your portfolio, it's nice to have a courses, but it's much more interesting to have a cases solved. So what we wanted to suggest to you, you're going to go through the basics code today, but if you find something more interesting, a solution and like recommendations what Elena will give you, will use some other processes, you can give us a link and say, hey, have a look, I solved it like this and it looks even better. We will give you a certificate that you solved the case, which you could put on your portfolio and show next interview. Okay. If any questions, thank you very much for listening to my introduction.
I have a question.
Yes, I'm trying to read it.
Yes.
So I think it's Elena will be better answering it. How to accommodate real-time data, seismic or another, that usually include to big data category in Python. Thanks. Elena, would you like to answer that?
Yeah, I think I will return a little bit later to the question related to Python after we go through code, just to have some ideas. I think then we can switch to our audience, because it was very interesting to observe who is listening us today. So I will share my screen now. Give me a second. Vita, can you see my screen? Just to check.
Yes, great.
Yes. Okay, perfect. So we can see that we have really broad audience today. It's a lot of people from Nigeria, a lot of people from Indonesia, from Italy, from Norway, and actually many different countries. So thank you guys for coming and joining us today. It's 81% responded to questions, and I saw online it's more than 200 people watching it right now. So, and it's, yeah, I think it's also interesting for everyone attending this event to see what audience is attending. And we can see that a lot of just graduate people who looking, possibilities in their careers. However, there is also a lot of people with a lot of years experience, 20 plus, 14 people. We have people from all disciplines. Yeah, one group is not presented, but probably they just didn't respond to questionnaire. So you can see everyone wants to know how to apply Python in geoscience.
Or maybe they're already journeying like inversion AVO with their rock physics and other disciplines. It's often comes.
Yeah, it could be combined under other field. So, and now, yeah, since we are having an event related to Python, we also wanted to know, yeah, what experience do you have, guys, in coding on Python? And quite a lot of people has limited experience. However, there's 3 people have 10 plus years of experience. It's really cool, guys. I have on Python because I switched to Python not so long time ago, before I was using languages. And yeah, and here's just some words which people typed in, which packages and models do they like in Python. And yeah, leader is pandas, because Python, of course, is very practical to work with big data sets and to do all manipulations with the data. And I don't know, we can go through the codes, questions very shortly. So the first one, I think Vita already answered. It was, yes. So there was a question that I'm a geoscientist interested in seismic interpretation, petrophysics and geomodeling. How can I link AE and ML to reservoir characterization and reservoir modeling being a beginner? I think
I will try to answer it if, as especially as a beginner, but does it mean that I'm just science interested in science interpretation? Are you just interested, or you already actually know something or work with this discipline? Because just to link it with no reason, it's not really necessary. Try to find the task which cannot be solved with traditional or conventional methods, and try to optimize it and bring it to more efficient way or to production that it's really needed. Don't just apply IEML just to apply. So please think first if it's really necessary.
Yeah, I think it's a great answer. True. Just don't try to apply the most coolest algorithm you ever saw. Try to see easier solution first. And if it's possible to solve without ML, then it's also possible. So at the end of the video, there will be a registration to review. I'm not sure. It's probably to review review the YouTube video. So I'm not sure about this question, but I assume that the video will be available.
Video will be available.
Yeah. So guys, if you will want to rewatch it, you would be able to rewatch it on YouTube. So this is very detailed question of a list of articles. I think the easiest way to recommend some articles is by if Vita will post some LinkedIn post, and you can.
And here also articles which subject related application of ML or RE to particular geo subject discipline, or are you still learning geo? So.
Yes,
I especially shared a couple of software that already today work into production. So have a look at them. Go through the video again and have a look at them. They have already some articles which you can go through and see how they solve things which works in the production. So it would be maybe enough.
Yes, so if you have specific question related to specific field of articles, just resubmit your question on the Mentimeter, please, and we can come back to it. Okay, this one I need to postpone. We will come back to this later. How far can we apply the synthetic training result?
On the synthetic data, or what do they mean? I would also like to add here, when we work, for example, in medicine, the cancer cells somewhere in Japan compared to normal cells will be similar to cancer cells, I don't know, somewhere in California. It's one deal. But when you work with the seismic, as I told you, sandstone on the North Sea and sandstone on the Norwegian Sea will be really different. And if you just learn on pure synthetic data out of wells, you're also minimizing the error by not including the noise in your data. So create your synthetic data and go to your real seismic and try to recognize from real seismic based on this synthetic. If that's answering the question.
So let's go to the next one. What type of inversion do you use? Is it pre-stack or post-stack?
What we used inversion, we patented this algorithm, and it will be released soon. We use algorithm from the family of artificial intelligence to help us to separate VP and density from post-stack data. In traditional physics and traditional understanding how the world exists today in geo world, it's not possible to do. So you have to bring this artificial intelligence techniques to do it. I will not explain it today since we are waiting when patent will be released and will be publicly available. It will be soon, and then we will show it. So you just have a chance to enjoy the output and use this data for your learning today.
So you just skip one step, but you are close.
Yeah, just skip one
final
step.
Solution.
If you don't have it, you still can use all these techniques what Elena will show you today, but instead of P and density, you can use P impedance, because you can compute on post-stack data P impedance.
Yeah, thank you.
In your recognition set, I mean.
Yeah, I think it's a good answer, Vita.
Thank you.
Of ways where we can combine AI, drilling, and geology in a single project.
Drilling and geology in a single project. I believe such cases existing, but I have not been working with that. I do pre-drill analysis. And just what we showed to you, it combines IE and geology.
So it's probably better to find a drilling specialist who.
Yes, and I saw articles already today. I think you need to go more to petroleum engineering. They have some real-time analysis while drilling, and they use already artificial intelligence techniques. I saw them, but I'm not specialized in it, so I can't comment much.
Okay, I see that questions are coming, so I propose now to switch from questions to our second part, coding and doing something by hands to see how it works with AI and geology. So I will switch my screen, sorry guys for this.
Then we can answer it in the end.
Yeah, we will respond to your, we will give a response to your question at the end of the presentation, don't worry. So, yeah, so Vita gave a short introduction about her field. Her field is geology, and my field is more programming field. And actually, I'm in the background mathematician. I did my master degree in Novosibirsk State University, the same university where Vita studied. After that, I had a short internship in Schlumberger, where I had first look on actually what geology is doing. Later on, I continued my education in Eindhoven University in the Netherlands, where I continued my study in applied mathematics and was doing some cool predictive models for Dow Chemical Company. After that, I was working for many years as a pricing analyst at Allseas, where not so much artificial intelligence was required. So like coding skills and all other stuff, I'm just doing as a hobby, and and applying it on a practice for projects. For the one I will show you, we are working with Vita. And currently I'm doing my MBA at Imperial in London, and I'm consulting Vita with my mathematical knowledge and machine learning and data science experience. So I think you remember what problem we are gonna look to today. And so we have some information about wells. It's measured data from wells. And we have some seismic data. In the first exercise, we will work with 4 wells only, where we have data about time, density, PV, and impedance. And as well, we have seismic data and 11 attributes from the seismic. And we are trying to predict oil or no oil, only 2 values, 0 or 1. So already from this description, you can see that it's a very typical classification model. And we will try to apply some typical models such as logistic regression, support vector machine, or Gaussian naive bias, and others. In the second exercise, we will modify task a bit, and we will use 7 wells instead of 4. Moreover, we will add some extra parameters which were measured in these wells. It will be porosity and clay. And we, specifically for this exercise, we will try more accurately work with the data. In this sense, like a mathematician like me cannot work so properly with the data only, because I don't have additional knowledge about geology. So I don't understand big difference between different type of layer of geological layers. So luckily, Vita has this background and she is actively involved in the project, so she can really advise me in the right direction, and she can clearly specify which layers we should choose and work with them. It's exactly the same as in previous exercise. We will just predict two numbers. It's 0 or 1 for oil or no oil. And in this exercise, we will add some extra features from ML. So we will use grid search to tune our algorithm for best set of parameters. And we will also apply K-fold. Just briefly, it's splitting your data, available data, in a K subset, and using one subset as a validation set and all other K-1 sets as a training set. And it's doing like it's moving from one to another. So you're using all data in your simulation and to build your model. And in the third exercise, it just it's what we want to see at the end. So we actually want to apply our model which we developed on the previous step, and we will try to apply it to 3D volume. We will use a pickle model and then plot a 3D slice. There's a lot of different packages in Python exist where you can even visualize some 3D, but due to kind of some inefficiency with all this algorithm, I cannot show you in a real time how cool it can draw anything, but you can find a lot of information online how to present your results. So now I will switch to Jupyter Notebook. I think you all received Jupyter from GeoPython team, and we will start with exercise 1. Just a second. We'll put it a little bit bigger so it's easy for everyone to read. So in the first exercise, we have 4 wells. We have some information measured inside the well, and we have seismic data with 11 attributes calculated from seismic data. So as a first step, we need to import all our libraries. So guys, go, if you can even combine and go in through Jupyter, it would be great, because then you can see how it's working and try it by hand. One of the first steps is always we are reading data. In this case, we have already pre-prepared data for you, cleaned it, and combined it in a way that it's easy to handle. Normally, you are given like SIGY files or some other type of files. So there's a lot of pre-processing of data is required to put it in the right format for Python to practically work with it. So yeah, we can assess our data. Just so we can see that, for example, logs, it's our data measured in 4 wells. We can see that there is no missing elements, and okay, in this format it's not very practical for me to work. I will just a second, I will change it. Okay. Yeah, and just to show you how data looks like. So you can see that we have columns time, density, P wave, porosity, clay. Water saturation, it's our target column. We have 1 and some other values here. When 1, it means that it's just water. When it's a little bit different value, we will try to make a criteria how we understand when it's oil or no oil. Then we also know log ID, so we know from which well this data is taken, and we know horizons, and we know impedance. We actually calculated it separately.
Elena, can you have a look to the questions on YouTube? There's some
Just
maybe a bit slower. So
yeah, okay.
the last.
Okay, no, I need to find the right screen.
They're asking regarding what you're showing right now.
Yeah, just a second. Okay, I will go away from full mode. Can you just send him this question to the chat in Zoom? I think it can be.
Seismic is 1D area along the well location. Seismic DF.
Okay, yeah, we will come to this one. I still want to look, guys. So yeah, seismic, it's our data. We can show how it looks like. Okay, I will go to bigger mode, then everyone can see. So no, it's correct one. So, a little bit. So you can see the second data frame which we'll use. So it's our data frame for the same logs inside the log, and we have data in time. We have information about time, about seismic parameter. We have log ID. So yeah, it's just a specific name for our log. And we have from each of this value, we also calculated 11 of parameters. Maybe Vita can add here like more description from geological way.
This is more or less standard attributes, the most often used. And instead of to create features and non-making sense mathematical combinations, we decided to try what if we use attributes which we actually know how interpreted. Will they add values to us in the recognition process? So we choose this standard attributes, I would say, from post-stack data. And also there is a question, how did you convert seismic 3D to CVS file, which can be read by pandas? We did it, well, with seismic processing company, we manipulate with data, whatever we want. SIGY file for this exercise, it would take a bit longer time. It was not that practical, so we just output it to the text format. And if for the first exercise you will have a full seismic section, then for 3D we specially cut it for you within one formation. It will be only 52 samples, right? 152 milliseconds by 4 milliseconds. And what we did also to avoid zeros in the text file and text format, we flattened it. So you will get one formation which is flattened to the zero, so it's a light file, and you can very quickly run through it. And then you can just take a time slice in your predictions and see if you, because the reservoir will be just in the center of your SIGY file.
Yes, so and in general, yeah, you can even read direct SIGY.
Elena, one more. They're asking where we can get the Jupyter notebook and the materials. Yeah, when you downloaded the data, Elena was making a note readme, so we expect that you are having already Jupyter notebook. Yeah, can you just give some directions for them? Where can they download it? And then the question, so they are not 2D or 3D, but 1D trace?
They are we have a 3D picture, but we can put like one on top of the other. So we can actually flatten it to make it 1D, because we always remember the name and we remember position of everything. So we can reconstruct even 2D picture later on, or 3D picture if needed.
It's just done for you to simplify, go through the task. If we would go through the real SIGY and real LAS, we would a LAS file for wells, it would be just taking longer time. So it's everything in CVS format. We already organize it, so you can just go through the task and see how it can be solved. But later on, we will put for you real LAS and SIGYs, and you can also dig into how to open them within the same solutions.
There's one more question I see. Why you choose time as series instead of depth? Yeah, you can choose both, but our SIGY files originally were with time. So
Seismic is in time. So we tie the wells and bring them in a time domain again for easy to make predictions.
But you actually will see that we don't use for our predictive modeling time time column at all, because it's actually makes results very unstable. So yeah, the first data frame, it's our log, so it's measured information from wells. The second one, it's seismic. It's related to exactly the same wells. And we have one other data frame, it's a section stack. Section stack, it's our 2D data frame, which we'll try to predict for nice visualization. And it contains the same data. So it contains time, density, P wave. It actually doesn't have porosity and decay. That's why we cannot use it in this exercise. But the rest it has. And it also has all these 11 attributes from seismic. So first step, it's always nice to visualize, or just to dig in the numbers, what kind of data you have and what numbers is there. Is there some strange outliers? Is there some missing values? I can say you that in this data set, you will not have missing values because we prepared this data that way. And there is no outliers. So we did pre-cleaning for you. There's one cool function in Python. So if you can import pandas profiling, and sorry, can you repeat? Yeah. So, but
Elena, can you do a bit zoom out? It's
yeah. Is it then too small?
Yeah, that's good.
Okay. Okay. I see. It's not fitting properly. Sorry, guys. Yeah, for me, it's this size is also much better. Okay, so it's So if you try pandas profiling, it will do a lot of work for you. You can do everything yourself by hand and plot all this 1D, 2D plots, but it will calculate a lot of information for you, and you can just go through a report and see what you have. So you can see it's summarizing some data sets, it's generating some report structure, and just in a few seconds you will get report. So it's just just practical tool. I don't know if you're familiar with it, but it's I find it very handy instead of doing a lot of coding yourself. So we can see overview of our data. We see a number of observations. We know number of parameters we have, and we know some information about like a type of correlations within the data. So we can see that density and impedance is correlated, and P wave and impedance is very highly correlated. Yeah, because actually impedance is calculated as the multiplication of density and P wave. So, and then, we can go to variables and see the distribution, some main parameters about mean, maximum, minimum values, and so on. So just scroll, guys, through it. When you have your Jupyter.
Elena, could you make a pause, please? Because some people just managed to download it.
Yes, guys. Pandas profiling, you first have to install on your, in your Anaconda. So to install it, it's probably you need to use pip, pip install pandas profiling. You can just ignore this line for now because if you didn't install, it will not work, but the rest of code should work there. Yeah, if it shows name error while executing pandas profiling, it means that you didn't install it. So go to your terminal and install inside the terminal. So the same way as you originally installed, for example, sklearn, or you installed some other packages.
And then how to handle poor, difficult, well-seismic tie. Don't tie it at all. Just check shot, correlate your logs, and that's it. And then you will have correlation between time and depth.
So yeah, I will return to, okay, someone is helping me and saying how you have to install Panda profiling. Thanks a lot, guys. So just go to your terminal and you can install it there, and it should work if you properly install. So yeah, you can see that porosity has some high peaks in some areas, but mostly it's just very okay distributed. So you can slowly go through each of these parameters and see how it works. And you also can see some interaction between each of the parameters. So for example, if you choose time and density, it will visualize you already how data look like, or how time and p-wave. In general, you even don't need to use this pandas profiling, but it just simplifies. You don't need to do this 2D plots, 1D plots, or anything by hand. So, and and it also shows correlation, and we can see that there is high correlation between time and density, time p-wave, and the impedance. You can also use some different type of correlations, and you even can just make this correlation matrix yourself by using standard plotting functions of Python. As I told you, there is no missing values, guys. So yeah, this report also shows that there is no problems with our data, and it shows example how data look like. In general, when you're starting working with code, and when you, for example, collected data about few wells, you really need to go through all the steps, clean your data, and prepare it to be ready for doing the work for you. Before, without cleaning, it's very difficult to start working and doing some algorithm on it. So yeah, now let's come to the data. Yeah, we want to, I made some simple function. It's plotting per log. We want to plot time versus one of the parameters from a log. And if you just run this code, and then you would be able to do some plotting of, for example, density versus time. It will show up, and then the same way you can do with porosity, and you will see how we have only four logs. So you see for each of this log how our data look like. So exactly the same, you will have porosity, you will have p-wave, so you can see what values you have. And if there's something strange, you really need to clean your data, or you will need to maybe scale your data, because it could be that data is received from different resources, and you need to prepare it in advance. So, and we now have our water saturation column. Water saturation column we will use to make our target column of 0 or 1. So in case we have 1 in the water saturation column, it means that there is no oil at all. But in the areas where water saturation is lower than 1, and we took as a limit, it's actually lower than 0.8. We consider this data to be oil, and we will predict that there is oil in this area. So, for example, for first well, 6507/2/1, we have like some oil on the bottom, and for other columns we have like for second well, which is number 4 on this graph, we have actually 2 areas with a little bit of oil, and for the next one we have 3 areas with oil, and for the last one it's it's approximately 2 areas with oil.
Elena, they're asking you if you could explain a little bit about the function syntax.
About function syntax, yes, guys. So it's you mean about function syntax of plotting function. So in general, what we are trying to do, we will pick up, because we have in our data all 4 wells together. So in every time we are plotting something, we want to have our we give into our function our data frame. We give column name. So in this case, for example, column will be density. And the type, it's just a shape of lines and color. So when we pre-select our data, so we select from a column loc ID. So let me add. So we know how our data logs look like, and we know that there is a loc ID column. So we can see what values it contains with count values. No, value counts. So we have 4 wells, and for each of this well, we want to take. So with the first line, we will take all the names of wells, which is 4, and then for each of them, we will start plotting a separate plot per well. So we are configuring our axis. It's subplot of 4 subplots, and for each well name inside the list of our data, we select only data related to this well, and we just plot our column name. In the first graph, it's density versus time. So in general, if you guys go line by line through the code or try to visualize what exactly each line is doing, you will be able to have, exactly understanding what's happening there. So in this case, it's actually, we don't have, we are more interested to see results, how we predict, instead of just going in details in each sub-function, which we used in this code. Since, we want to see application of geoscience to Python. And with each of this sub-function we defined, you can just go by yourself and figure out how it works. It's a very simple functions. So after we will visualize our data per well, we also can do some pair plotting in just a very simple line in Python, and it will show you all combination of our variables. So for example, it will show you time and density on the second spot in your grid, and so on. So you will just see if there's direct trends you can already notice from the data. So for example, if we look on P wave, and the last parameter is impedance, you can see there's a kind of very linear relation between them. And if you look on the density and impedance, it's not really linear, but it's like, there's still very kind of dependency between these parameters. So normally you really need to visualize a lot before you're starting to apply algorithms. If you see some strange pattern in the data, you have to remove some data from your training set and from your data at all. And yeah, so spend a lot of time on visualization, because without proper visualization, it's going to be difficult to use what you get in your models and to interpret your models. So, I see there's a lot of help comes from guys. Yeah, thanks a lot. So actually, yeah, the next line, you can just run it in your own time. It will be quite cool visualization. So just uncomment this line and run it. It will take some time. So I will not show you, but just if you're patient enough, it will visualize you all these plots as above, but per each of log name. So if you will check our data, we can see what step we are using. In a seismic data frame, we are using a step of 4 milliseconds. However, in a log data frame, we have completely different time step. It's way smaller because it was a real measurement and it's taken more often. So we need to align our data with two different data frames. We cannot use them just to, when we are not combining them in a proper way. So we need to decide which time frame we will use. And in this sense, we decided to go with moving average and averaging our log data with a step of 4 milliseconds. I see there's some problems still with panda profiling. So guys, just don't use this panda profiling. And in the first line where you export libraries, just comment this line about panda profiling, and the rest of code will work without pandas profiling. But you will need to make all these graphs by hand. So just Google how to install pandas profiling. It's it's specifically for Python. You really need to Google a lot, and if you can find how to install panda profiling, it will be very helpful for you. So yeah, about moving average. So we decided to make a moving average on our log data frame, and just averaging, for example, density with a step of 4 milliseconds or porosity with 4 milliseconds. To do moving average, you will need some kind of some extra functions, because it's not just directly existing function in Python or in the pandas. So you just need to write some mini algorithm about how to change way your data frame is presented. And in general, we were just averaging. So for example, if we see the time, which is 514, then we are trying to find the closest time with a step of 4 milliseconds. So I think in this case, it should be 512. Which is which will be the average time, and we will average time for many of them, and then we will use aggregate function or group by function in pandas, and then we can group by everything like in the same time and find average value of density in this area or porosity in this area. So in this sense, if you are trying to do some ML with Geo, you really need to know how Python is working and how algorithms are working, because there is a lot of mathematics required to process data and prepare data in a correct way. So I do not go inside this function. It's just sub function to prepare average. So if you execute these lines, you can just do any of this step by yourself and see what exactly happening with data. And and at the end, so our blue blue color is presented our original data, and with red one, we present how our artificially averaged data will look like. So at the end,
just add why you're doing that so they can understand.
Yeah, we are doing it only because our seismic data has a 4 millisecond step when our log data has completely different step. It's way more data lines in between, and timing is more, yeah, we just got a lot of more data points in this data. So we need to have a time column in exactly the same format in both data frames, otherwise we cannot combine them together. So yeah, when we made averaging of our log data frame, we can combine data frames, and we are combining them together by using function merge. And we are specifying log data frame average with seismic data frame. And we will combine on 2 column names. It's log ID and time. And all other elements which is existing in both this data frame will be, okay, I need to go for a second to run this lines, otherwise I cannot show you how it looked like. Just give me a second.
Elena, there is a question. Is it normal that I don't have any figure outputs? I don't have errors when I run in the plotting cells?
If you just do a simple plot XY, do you get any figures? You normally have to get figures. It's might be that it's very slow for you, or you have some problems with Python installation. So in general, let's go a little bit further with this exercise. I understand that here is a lot of questions coming about specifically how this code is written, but it's yeah, it's practical if you guys will dig into code at home by yourself, because you cannot explain this code within 3 hours. It takes much longer time to write it even. So briefly, why we did averaging, because yeah, our time step was different and we could not merge our data frames. So now we have exactly the same time step and we can merge 2 data frames, our log average data frame and seismic data frame. When we combine them together, we have one single data frame with many columns. It's 21 columns. And these columns are coming from both of these data frames. So you can see that we have P, density, P wave, porosity, and so on. And at the end, we have all other columns which are coming from seismic data frame. And this data frame will be our main data frame, which we will use for applying some ML algorithms on it. So, and just simply showing, yeah, we have exactly the same well names, and we have way smaller number of rows per each well, since we did averaging there. So in case we just look on all the columns and we can see yeah, which columns existing in data frame. So first step would be like, yeah, let's apply all of this column for prediction, because we have them and probably they bring quite important value to the algorithm. So we will not remove any column yet. So you can also plot Pearson correlation, and you will see which elements are correlated a lot. And we can see that, for example, a seismic column and AWCP you have correlation 1, it's not always good to have correlation close to 1 or -1, because some algorithms are very sensitive to correlated columns and can give very bad results. So in this case, we just removed this column AWCP. But you can try to keep it and see what is difference with the results. So yeah, it's just visualization of this column, and you see it's really almost linear dependency between them. So we just removed it. Moreover, we know, like, from our horizon column, which horizons to use. So in this case, it's extra knowledge from Geo is required, and luckily Vita knows a lot about geology, so she could advise me which horizons to use. And we are using only 3 horizons because this horizon is mostly containing oil and gas. And yeah, in other areas, there's nothing, so we just ignore this data.
I can share here just a bit. So if you just take all your well and throw it to your model, it doesn't give you such accurate solution if you split the well into formation and start to predict within the formations. Then it's almost straightforward. So that's what we're doing here. We're splitting our seismic and we're splitting the well data by formations, just to simplify it.
Yes. So, and now it's our machine learning starts. So main part of it, we prepare data. So we have our data set, which we can use for learning. And we need now to split our data into train, validation, and test set. You probably learned a lot of algorithms, so you know why we are splitting it. We need to learn on some data, and we need to validate it to see how good it's working, and we will just keep test subset for final validation, which we actually cannot use to improve previous tests. It's just our reference points. Are we doing good or not? So, and in this case, we will use well number, ending on 4 as our test well, and all other wells. So 3 of them only we will use to split into train and validation set. So we define our test well. We give target value for which values of water saturation we will count as there is oil, there is no oil. And in this case, we are using 0.95. It's quite high value, so you can play with this value. You can change it to lower value and see how results change. And in this way, with this line, we are defining our target column, which we are going to predict. After that, we are taking, kind of reforming our data frame, and we select our test well part. So we are searching for all logs which are of a type of 6507/2/4. It's our test well, and we're taking this one as a test data subset, and the rest of the well, it's our training validation subset. And in Python, there's a lot of pre-existing functions which simplify life for writing a code. So for just splitting into test and train data, you can use function train test split. And you provide this function with X data set, Y it's your target column. So in this case, it's our target column. It's even called like this. And we have test size, it's 30% of data. So we're splitting our data into 70-30%, and we will use random states that our calculation will be, we can repeat exactly the same calculation, but you can choose any other random state. Can you please explain the abbreviation of the features? There's a questions. I think it's mostly related to.
I'm doing that. I will write it down.
Okay, you're writing it there. So it's probably a question related to 11 parameters, attributes of seismic. So yeah, when we split it out data, we can then move on and start building pipeline. Pipeline is simplifying for you a lot of handwork, plus it also helps for you to operate exactly the same with all subset of your train validation and test data. So you have exactly the same scaling and you're not making mistakes in the scaling if some of parameters is scaled. And since we are having numerical columns and we have categorical columns, numerical columns, it's most of them, and categorical, it's only one column, it's horizon, which contains the name of horizon. So we will use a little bit different data scaling or data manipulation with each of the column. So we will use column transformation, and we will transform our categorical column, numeric column. We will categorical, it's not numeric, sorry, a categorical column, so it's a horizon. We will use one hot encoder. Well, and it just means that, like, yeah, when you have some specific value as 2D K65, it will have ones at this specific column. So if you have 3 different horizons, you will at the end get 3 columns, each containing this this specific horizon, and only indicator if we have row corresponding to this horizon. And for numeric columns, we will use standard scalar. You can use any other of them, but yeah, standard scalar is one of the most applicable here. And it's scaling properly all our data. And we don't have we don't have to worry about the type of the data we are working with. And we will apply the column transformer on our specified transformer function for each type of the columns. So after we did this work, we can start going directly to our logistic regression, for example. Since we have a classification problem, we will start with the easiest one, and the most standard one is logistic regression, and we will try to see how logistic regression is working. Please give me 2 seconds because I need to run this code. Otherwise, I think I will not be able to visualize final results. So in logistic regression, we
Elena, just a second. They're asking, does it matter if we change the random state number?
No, it doesn't matter, but you will not have exactly the same pictures as I will have. So random state is just specifying you to have a repetitive result. So it's actually not completely random state, and random value will be generated in specific order. So we are using 42. You can use some other number, but then our final pictures will not. You will have a little bit different picture, but it's normal because you used different state.
And one more. Could you explain why are we converting the columns data, float 64, float 64, and so on?
So it's I need to find which one exactly, but so in general you want to have columns in the right format. So if you have numeric columns, it should be in a numeric form. It should be or float 64 or should be integer 64 or 32. Because if it's written as a string or as an object, you cannot do some manipulation as summing up your columns or doing any function in which you can use numbers. So just when you get your data set, go through the columns and see if they are in the right format initially. There is a question, I think, to you, Vita. It was a tied to the seismic data prior to modeling?
No, we will not tie the wells here. As I was mentioning before, we were thinking how to address the problem. We need some kind of compaction trend, or we have to look at the lithology changing with the depth, because you do have this compaction. So what should we use, time or depth? And you will see in the end that we actually didn't use this time trends. So we use only the real values. Since we have more reliable information to recognize from, there was no needed to go for time and depth curve. So we didn't tie the wells here. This is just exercise for you. So first we went through, should we tie, should we find compaction strength, and etc. And then we came to solution that we don't really need it. And the same with this choice of the attributes. We tried just to generate some kind of features that was not working so well. So then we asked, maybe we can take seismic attributes which make more sense if you geologically interpreted them. For example, you know that like instantaneous frequency have some kind of shadows, empirically noticed it sometimes below the reservoir. Maybe that will help us if we produce the same attributes from the synthetic trace and the same attribute on a seismic trace. Maybe we will have some kind of better correlation between these features. So you can choose your own features. Yeah.
Okay, so and I think there's one more question about like criteria behind selecting attributes of the seismic. So 11 attributes. Can you hear me?
Can you repeat one more time, please?
Yeah, any criteria behind selecting those attributes?
That's what I was just saying. So it's okay. We tried to in the beginning. Remember, we was going through some mathematical combination. Then we decided to go for some more informative features, kind of. No, you can choose your own attributes. It's just for you for exercise.
There's a question: why to apply column transformation? It's enough to have all variables, so for example, in integer format or in binaries for categorical. Yeah, column transformation, it's actually not just changing format of columns, but you can have some columns like in 1,000 and some of the columns will be like 0.1, 0.5. And of course, the columns which has like 5,000 values, they will try to tend to change your algorithm. So you really need to scale everything in interval, for example, 0, 1 or -1 to 1. It's just mathematics behind this, because algorithm cannot work with very different scales of parameters. And when you have very small parameters, it will be neglected by algorithm and it will tend only to work with thousands. So your columns, which is very small, will be lost. And for like categorical columns, we cannot use just words in our algorithm. Our algorithm doesn't understand words, so we need to specify. If we have like 5 categories inside the column, we can specify them as the numbers 1, 2, 3, 4, 5, and then we developed like actually 5 new columns where we allocate like 1 only on specific rows and 2 only on specific rows. So it's just how Python is implemented and how it works there. So because there's a lot of pre-existing function, so there's some rules how you can use this function only. Is it possible to have feature importance by model after training? Yes, normally model will show you which features it believes is the most important, and you can visualize it. You can even do it without training. You can use some principal component analysis, PCA, and you can easily implement, and it will show which features will be, have more values. So now we are actually finally coming to to apply our first classification model. It's logistic regression, and we define it as a pipeline. You can do it without pipelines just by specifying logistic regression, but you always have to remember that you need some column transformation, and then you need, as a previous step, to a separate line to specify column transformation. So, and we will just apply logistic regression without really specifying a good selection of parameters. So we'll just specify maximum number of iteration and which solver we will use, and again, random state to have repetitive results. So when you specify your logistic regression, you can also fit it on our train data. And we have X train and Y train. So by running this line, you will have, algorithm will learn and will remember the structure. So you will be able to apply this algorithm already on our validation set. So yeah, if you run the next line, it will actually apply this algorithm to all training data, to validation data and test data, because we actually want to see how it's performed. Is it performed good or not? And then next step, you have to decide which metrics to use for kind of evaluating your algorithm. And if you just use accuracy score, it will say that it's like, yeah, with almost 0.9, it has perfect results. Normally, yeah, 0.9 is actually very high accuracy. But you remember, we have a lot of zeros and only a few single ones. So in this case, yeah, even if we just give to our accuracy score function of real values and say that our predicted column is all zero, it's already will give very high accuracy. So just accuracy is not very good metric for classification models, especially with such kind of not equally divided 0 and 1s. So we will use precision recall and F1 score. It's different metrics, and it helps you to really identify which of group is predicted correctly and which one is incorrectly. So we mostly will look on our F1 score just for simplification, because we just need one single metric there. And then, yeah, so we did some extra functions. We wrote some functions. So yeah, it's just will help you to visualize all the results. So it will show you some precision recall and F score for each of your algorithm, and it will, yeah, and we'll just give directly F1 score evaluation. Its function exists so it's just without printing on a screen. So, and we also want to do some plotting. We will plot our real values versus our predicted values, just for your visualization. And you can rewrite this function completely differently. It's just for simple way to see what's happening there. When you're applying, this supporting function, and we are using it, it's called precision recall F1 score train validation test. It's showing precision recall F1 score on all these three sets, and it's also visualize all these three sets. If you run this line, you will see that, we have some precision. First one, it's precision and recall for training sets. The second one, it's for validation set. And the third one, it's for test set. And we see like, okay, here precision, it's 0.66, recall and 0.2, and F1 score is 0.3. It's actually not so good result because, it's performing quite poor. It's not really highly correctly understanding oil position, and and you can see if we are going to validation set, it's giving completely different combination. In reality, we need to have very close values between training set, validation set, and at the end we also want to have almost the same values on the test set. And if you see how it's visualized, so the left one, it's our training set. It's data on which we learned on a logarithmic regression. And yeah, in general, it's recognized quite well with no oil, and it doesn't recognize so well where we have oil. It's only recognized some areas, but it's missed, for example, big area at the bottom. And on the validation set, yeah, it's actually almost didn't recognize any oil properly. And on the test set, it's just completely incorrectly. So we can apply some other algorithm, for example, Gaussian naive Bayes. It's written similarly. Instead of classification function logarithmic regression, we will use a function of Python, which implements this algorithm, and then we will fit it on our data. Yes, or let's go to the end of this exercise. So in general, we have like, okay, we have now a few different type of classification models. So you can run it in your time and you will see for all of them, like how it's visually look like. And we just, you can go through all of them because time is running through, and you will see how they work. And at the end, you can also try to use one of these algorithms or all of them to predict on 2D, because we had one third data frame at the beginning. We loaded it from a file. So, and when, for example, we apply logarithmic regression on the current features and how it currently works, yeah, here's a picture. It's oil almost everywhere. Blue, it should be oil. So we have really very cool reservoir. So, but in reality, it doesn't look like this. So you cannot just find a reservoir everywhere. So we see that, yeah, algorithm doesn't work well. And we also saw it by our metrics. And you normally will ask question, yeah, how to improve your algorithms. And I think we can work on improving this algorithm after a short break, like for 5 minutes, yeah. So what time is it now?
You should have a
Okay, perfect. So are we live now? Yeah. Okay, thank you guys. I understand it's very long afternoon for you because we are already almost 2 hours on this video call, and yeah, it's great that you are still following us and still asking such a great questions. It shows your interest, and we understand that you actually very much into this topic. So let's go a little bit shortly through the question. So I saw the question from Ahmed. Is train test split by default shuffling data? Yes, it's actually shuffling data randomly. So we will have in our train data some elements of each well, and we will have in our validation set also some data from other wells. It's maybe not the most great way to do it, and it would be nice to actually allocate one well as a validation set, but since we have only three wells which we are using for building models, it's just too limited data, and we cannot separate one well completely. So in this case, we were just using a train test split, which is shuffling data. Integer should not be used for categorical, because when we use integer, computer will think category 10 is more valuable than 2. Yes, you're right. That's why we are not using it. We are not rewriting them ourselves. That's why we are using one hot encoder. It's an algorithm which will take into account that category 10 is not more valuable than category number 2. Do we need to see the training data fitting as recall for training set is very low? Like, what step do you recommend for better F1 score? Yeah, we were just visualizing training data just to show it's actually already not good on training data. And to improve on F1 score, even on training data, you need to do some clever sub-selection of features, maybe generating new features, maybe manipulating a little bit data. We have very limited amount of points with target 1, which is not good. And you can use some algorithms which will reproduce you more data with point ones. It will just copy extra lines of this data, and then you can make balanced data set. So there's no way to know in advance which way will improve your F1 score. You just need to try a lot and see which one works for your specific application. Gaussian naive bias, is it also linear model? No, I think it's not really directly a linear model. But I think you can find this question just on Wikipedia. I don't remember exactly if it's from a group of linear models. There's still a question about where we can find notebook. I think if you guys subscribe to the event, you probably received the link to the data set and notebook code. Otherwise, you will get a link after this event as well. Yeah, there's a comment about you can use dummy index so that the integer value is not assigned to the categorical data. Yeah, dummy index it's very similar to one-hot encoding, but it's just try both of them and see which one works better for you. Can you explain the validation data set? So validation data set, for example, on this graph, it's actually for training set and validation set, it's our combined 3 wells together. And then we randomly allocated some 30% of points to validation set. So that's why it looks very similar, but intensity of points is actually different. And we have some gaps and there's no point because randomly no points of this interval was coming here. So a better way, if you have a lot of data, allocate just some specific values to validation set. Don't use just random splits there. So the next question is a good one. You mentioned that you have much more zeros than one in sets. This makes skewed data. Doesn't it affect the model performance? Yeah, it affects a lot because actually model will be biased for zeros, and you can use some techniques to get more ones in your data, just by copying exactly the same rows with ones and making proportion of 50-50 for both water and oil. Is it strange we only see underfitting, no overfitting? No, it's not strange. I mean, why you expect overfitting here? I think, like in general, we see that the algorithms didn't perform great at all. It's actually it's actually overfitted on one algorithm. If you go to MLPC classifier, you can see its precision is 1. So when we have 1, we would say it's we overfitted our algorithm because it's recognize only this specific type of our class, but it doesn't recognize second one. Second one is completely, it's with 0.33. So I think I will come back. So we had example when we used, all our columns available in dataset, and we were able to generate some models, not really good one. So we just use them as a visualization tool for you guys to see how the code work. And we can see that, it's not really what in reality you can find in geology, that full area, this area is completely full with oil. No, it's not such a example we gave to you. And the next question, how we can improve it, that algorithm will recognize location correctly. And if you go to the last plot, you will see that it didn't recognize almost any oil. So one of the idea is actually pre-selecting your features more accurately. Now we put it to our algorithm, all our features. I will come back to the top where we specify the features. It's somewhere where we, just a second. So we had quite a big amount of features. So you can see now in a line, in this line, I think it still should be 20, 21, 22 somewhere. So we had we had time, we had 3 parameters from measured parameters. We had horizon, and we had seismic column and 11 attributes from seismic. It's nice, impressive, a lot of parameters, but it doesn't always mean that we need to use all of them. So in this exercise, we will try to remove some of the parameters. And if you go to the line where we define our test split data, and you uncomment one line, it's already pre-written for you. So you pre-select different features. And if you will run this line, unfortunately, since it's rerunning, I cannot say exactly the column, but it's second line after split data into train, validation, and test. So if you will specify which features you want to use, in our case, we will just use only density, p-wave, impedance, seismic, and horizon. And we will run exactly the same algorithm, but only with these features. Yeah, there's a comment. I recommend you run feature important beforehand. Yes, it's normally the step you should do before, and a lot of people just skip this step, and then they try to to run a very extensive model on a lot of features, but it's not always good. So yeah, if you run code from this line, so I just run exactly the same code, and we have only a limited amount of features. And let's see to the first results. So we have our logarithmic regression, and yeah, we see precision recall still very unstable and not okay. And if one square is 0.3, it's not really great. And then when we go into validation set, it doesn't recognize anything there. So yeah, it didn't improve our algorithm too much. However, yeah, we will just go through all of them, and you can later on look on the numbers in details. So, and now we're starting to plot our 2D areas. So now we have our prediction on logarithmic regression on 2D. And we see that, yeah, now it's not so intense blue as in the first trial. So we see that reducing number of features already a little bit improved, but still it's doing something strange. And yeah, for all others, it's also doing something. Yeah, it's finding some other areas where it should be oil or not. In some cases, it's removing some areas. So here it's very difficult just only from mathematical point of view or say, okay, it's a good prediction. It's actually, we cannot say from mathematical point of view because our precision and recall is very poor on this example. So, but I think on this plots, it would be nice to have some comment from Vita because she knows more background exactly.
Yes, of course. If you just scroll a bit down. I think here Gaussian F basin was already doing some good job because on the top layer, it indicates correct prediction and you see the strong indication within the one big layer in the middle. It will be filled up with hydrocarbons, and remember we are predicting only 0 or 1, so we can't say it's commercial or not. Maybe it's not a recoverable reservoir, but it's already start to allocate properly places where we know where it's drilled and we know that it's hydrocarbons there. But you should keep in mind that we are having only 4 wells, and it's not much data we're learning from. And in the bottom, we don't have any wells at all penetrated, so we're just within different formation, trying to bring models from top upper formations and recognize on the bottom. So it's geologically also a bit incorrect. But for the shallow part, start to work better. And if you go down, in another algorithm was, yeah, here we go. So it's, or even maybe, yeah, here, we definitely know that just top blue, yeah, this one, it's hydrocarbon on the left upper corner as well. Left. This one, and this big layer is still this indication of oil. But again, this is just for learning exercise. It doesn't still do the good jobs. We need to bring more wells for training. And in the 3D, you will see that. Maybe you should a bit more faster. So you have all these codes and you can go one by one in the steps command self and try to play with it.
So yeah, in general, yeah, Vita is right. So it's just initial kind of direction for you guys to play with this code. You can try selection of features, which is more important, which is a more, gives more information to the model, and try to build new features or run it differently, apply different algorithms. There's way more classification algorithm you can apply. And yeah, as we already mentioned, yeah, the data is split on 0 and 1s like unequally. So you can do some manipulation with the increasing number of ones in your data set and rerun the code. So it's actually, yeah, just starting point for you. It doesn't show great results yet, but there is some point where you can improve it. And I think it would be interesting for you guys just to do it by yourself and to get maybe even better results. And if you have really interesting outcome of your simulation, please share it with us, because we would be really happy to see what algorithm you applied, what features you developed, and yeah, how you actually did it. And from here, I will switch to exercise number 2. So exercise number 2, it's very similar to exercise 1, but the only difference is, okay, just a second. I will go to the question, because switching to exercise number 2, maybe it's too fast. There's a question about, is there an option in sklearn to use other logistic regression method, like stepwise or forward? Go to the description of logistic regression function in sklearn. If there's this method implemented, you would be able to change these parameters. I don't remember by heart what parameters logistic regression has, but you can easily access it and yeah, and modify your algorithm. Is this section view an image seismic like GPG file, or converted SIGY file to some format? So actually 2D data originally is provided in SIGY file, or it can be provided in text format, and you can transform it to a data frame. So we gave you a data frame, and you are able, working with data frame, and plot it as 2D area. Can we show cross-sectional overlay with Payson and no Payson classes at well location? It's a question addressed to Vita.
If you go to in the beginning to my presentation, you will see 3 slides where we show how it looks like, where the original seismic with horizontal wells, and I indicate there where hydrocarbons are, the real places, and then the section with from the exercise 1, where you can see how it's predicting. And the same for exercise 2 and 3, you have outline of the reservoir 3D, and you can see how your prediction works. So for exercise 3, it's the most accurate predictions for the hydrocarbons you can see. But you probably will need to go back in the video and have a look. Or maybe we can later send all participants some slides so you can keep eye on where the actual hydrocarbons are when we're predicting. Maybe that will help.
Yeah, and there's one more question. Cannot we merge physical model with the ML model? Something not entirely, NN model, but guided by physical model to respect physics. Not sure how you want to do it. Probably there's possibilities, but you need to maybe be able that physics is described in some features proper way, or some extra feature generation from physical perspective of the problem. Because all these ML models, they're just written for very general way, and if you want to change something, you need to be very creative with them. And mostly you really need to be very accurate with your features and with your data given, and maybe pre-selecting your data or developing new data sets.
Yeah, I agree. Yeah.
I think we can now move to the exercise number 2. So in exercise number 2, we have the same four wells, but we added 3 more wells to our data, and we will show you how we modified our algorithm a bit. So yeah, we again just extracting our libraries. So okay, in this exercise, I'm not showing you this visualization of all plots because we are still working almost with the same data set, and you are able to do data exploration by yourself. We did it, but we don't present it here. So, and then like with this second step, we just create in some folder for where we will save our models when we will create some models. And for this exercise, we need to define few parameters. So interval, it means like we will use only specific interval of our like data. So it's just some small sub layer, very accurately defined because it has very similar properties. And WS level, it's water saturation level. It's 0.8 in this exercise. And we originally will not do grid search and k-fold, but you can do it, and this part exists, and I can even show you how it works. So, and also you can specify how many folds you can generate. So we are loading our data. It's again our data from wells. It's okay, here it's written called different stack logs, but it's seismic data with 11 attributes. And stack section number 2, it's just a little bit different 2D area for final visualization. And we will similarly define our target value when water saturation is lower than 0.8, it would be oil. And if it's higher than this value, then it's water. So if you print what columns do we have in the data. So we just show data. So it's our logs, and we can also print seismic attributes names. So it's our seismic data in stack logs data frame. So you will see that it's just the same data as before. Only the difference, we have extra 3 wells. New one, which we have not seen in the previous exercise. Difference with the previous exercise, we will now like push our models to work only on very specific interval of data. So for each well, we will define like which rows to take. So, and for example, if yeah, here is actually it's related to time. So if time is between 1300 to 1352 for well 3.6, then we will take this data. If it's other intervals, we will just ignore the data. And for each well, we'll pre-select specific interval. Maybe Vita can explain why these specific intervals were chosen here.
So this is the formation tops for each well, and we will learn from the wells within this formation, and then we will recognize on the seismic data within the same formation. So we pick horizons on the seismic by knowing that it's correct formation. That will just limit your error to learn on the wrong rocks, simply speaking, and to predict within the correct interval. And that can help you avoid to use some compaction trends or time depth trends. You just work within the interval. So if it was already compacted and it's a deeper line in a layer, you already will bring it to your learning model, these values. Or if it's much more shallow and more porosity, you again will bring it to your value. So we're learning with information at the wells and recognizing with information at the seismic.
Yes, so in general, yeah, we just pre-select this information like we pre-select these intervals for each of our wells, and so we just take subset of our data. And if you look all water saturation existing right now in our sub-data, we will see that, like, yeah, there's only oil somewhere at minus 2,750 exist. So around this area, there's no oil on the top layer and no oil, yeah, only in this bottom layer. So yeah, just some ideas to understand how many 0 and 1 we have. So yeah, you can see that we have like 4,000 data points, and only like only 170 of them has a indicator of oil, which is a proportionally very low amount. So you can definitely do some creative way of of trying to avoid this bias by algorithm. And we also can go and see what is different between our new wells which we added to data set, and just kind of print some information about these wells, and you will see that actually 2 of 3 wells has no oil at all, and only 1 well has some formation of oil. So here you will see some additional line of code you can play later on with it. It's just a opposite moving average. So in first exercise we were trying to apply moving average to reduce number of data points, to have a step with 4 milliseconds. But in this exercise, we're actually doing it the other way around. We are introducing extra lines to be able to use all original measured data, for example, from a data set, or to increase number of points which exist in a data set. And we will, so we just do some manipulation with moving average and opposite moving average. And when we are applying like moving average, we selecting one set of features, and we apply when we are not using a moving average, we using different feature set of features. So in our case, right now we'll use only 4 features. It's feature density, p-wave, porosity, and impedance. You can see the difference. So now we have extra feature porosity because our 2D data set also has this parameter. In a previous exercise, our 2D data set didn't have this parameter, so we were not able to use it at all. And we will split similarly our data into train, validation, and test set. In the test, we are using exactly the same well as in the first exercise, just to be very consistent and don't mess up with information we have, because we cannot use the information. We actually cannot know anything about this test set, and it's our just final reference point. So we can see how many values for each well do we have. It's not so many for new wells, so we have only a few points there. And and we can see our columns in data. So features, as I already told, so we only have four features. Looks like not a lot, especially when we completely ignoring all seismic information. And again, we are dividing our data into test set and our train set. And again, this train data frame, we will split it in train and validation subset. Similarly, as in the previous exercise, we are having our numerical and categorical features, just for simplification of using some transformation on it. And actually, it's exactly the same function as in the first exercise, so you can just go through all of them. And we are coming to the most interesting part where we are building our pipeline. First, before building pipeline, we are applying again this transformation. So for categorical, it's one hot encoder, and for numerical, it's standard scalar. And then we can define all algorithms. You can define even more algorithms and play with them and see which one works better. So we will use again logistic regression and Gaussian naive Bayes and support vector machine and gradient boosting, some mistake here, classifier and multi-layer perception classifier. However, you can see that we define some parameters at this step. These parameters will be needed when we will use grid search to find better subset of parameters of algorithm. And you can go to each of the algorithm like logistic regression and see what parameter you can change there, and also define them here and see which parameter will be the best one for your model. So for all of this algorithm, we define some subset of parameters. And now we're actually ready to run some prediction and build some models. So we will use a logistic regression with no parameter tuning. So it's just simply using very standard logistic regression with the initial set of parameters, and we'll apply it on a training and data set, and then see how it performs. So as you can see that, we get very poor precision recall and F score. And we don't really look on our results of test set because we don't know the set, and we cannot use this information to improve our training set. So how we can improve this one? So what we did, we just used the logistic regression without parameter tuning, and it's not always good. You better spend some time to find a good subset of parameters for your algorithm. It's not the parameters of which algorithm develops, but more it's starting like points where algorithm starts working. And since we already defined a subset of parameters a few steps above, we can also run grid search on this data set. And so we will use grid search function where we provide our algorithm name, and we will provide our subset of parameters of this algorithm and our training set. And then we will visualize the same results. And just by changing parameters of your logarithmic regression, we already can see improvement. So we get precision of 0.73 and recall of 0.65. Which is compared to the previous step is a really great result. And even compared to the first exercise, it's already way more stable results. It's still missing some oil point or predicting extra oil point, and we can see it on these graphs. So it's actually seems that there's more oil than in reality, but it's at least doing some good job in the right direction. It's still not perfect. It can be improved, and but it's showing right direction to us. And when we visualize it on a 2D element of data, we find like a very thin piece of like a slice in where we expect some oil. And maybe Vita because she knows this formation a little bit.
This is the 2D section from the second exercise, and it goes through reservoir, and there is a well there, but we didn't use this well in training, so the wells was quite far away, but within the same formation, and it gives already correct place where hydrocarbons should be. It's exactly there. So again, I think We should have included some couple of slides so people can go and see the picture and the map where this line is. Maybe after this exercise, I can switch to my video and show, so you can have overview and remember where we're located.
Yes, we can.
It will be the same picture, yeah.
Yeah, so we will show a little bit later where actually wells are located, but they are located in different positions. So one well is approximately here, one is here, and there's no wells in our training set close to reservoir at all. There's a few questions in the charts, but I will come back to them later because we have very limited time right now. So this one other next step to do, it's actually to, now we know how to build models, and we even know how to apply grid search. But when we are applying grid search, we actually not using full data set, we're still only using subset, and we want to use all our training wells. So to be able to use all of them, we can use k-fold and also with grid search together and see how it performs. So when we apply k-fold on logarithmic regression, logistic regression, sorry, so we see that it didn't improve a lot. It's it's still 0.7 and 0.6 for precision and recall, and almost 0.7 of F1 score. On this plot, you will see exactly the same train and validation set, because actually when you're using a k-fold, you don't have validation set. It's in every fold, you have like a piece of data which is used as validation, and then on the next one, its next piece of data is used as validation. So you can just ignore this middle picture, and we're comparing only a train set and test set. And again, we are plotting our 2D section results, and we have like, again, we recognize our oil reservoir in a right position. Still not optimal, still enough place to improve your algorithm, and it would be your like free time task, because I think it's quite cool. You have data right now and you can play, and it's real data from North Sea. So try to improve performance of this algorithm.
Norwegian Sea.
Norwegian, sorry. Yeah, it's true, we are working in different seas. So, and then we have other algorithms, so we can apply exactly the same step, like run without parameter tuning, run with parameter tuning, or do k-fold on all other algorithms for classification problem. And I think now we can switch to question a bit. Don't you think you should have fluid substituted your wells with brine to challenge your code to allocate oil instead of biasing the model by constrained well that have already oil shows?
No, it will be just complicating our task. It's not necessary. You can have wells as they are and learn from them, just increase the amount of wells. Elena, maybe you can share the slide from our presentation, because you have our presentation where we have task 2, predict hydrocarbons from inverted volumes today. So then they will exactly see where the line goes in a map, in a space.
Yes, just
quickly one slide, and then you will see where you are, what kind of wells we are using, where they're in the space, how far they are from the area where we're trying to predict the oil.
It's still opening.
Yeah, just switch to presentation.
Yeah, but it's opening presentation. Do you already have this one on your screen, this slide?
Yes, it's in the presentation time, what I was showing. And you have...
Which slide is it? I now have it.
It should be slide 24.
24, okay, let's move it here.
It should call task 2.
Mm-hmm.
Yeah, this one. So you see, here's the map, a small map with a blue line going through the long red reservoir with the gas. And this is the line showing the section which we predict. So our learning parameters are shown on the left side. Recognition. We're recognizing from this, yes. And prediction by different algorithms on the right side. And you see the well 654753. We have not used it. There is a space by arrow, blue arrow pointing to the map. Elena, can you show?
Yes.
No,
Yeah.
to the another map, the map where the red reservoir outline. Yeah, and this blue arrow showing, yes, down, 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 down.
Oh, okay, it's here.
Yeah, here's one. So we didn't use this well. The well is existing there. We use yellow dots wells in the learning process. And this well is particular located in the reservoir, which we managed to predict. So now you have kind of overview where you are and what you managed to achieve in the second task. And of course, tune your parameters, play with the data, get a better prediction. And you see, since 2D line, it's supposed to be like long predictions going up to the hill, kind of. So you're the last algorithm predicting a bit more than necessary, but I believe this ML classifier works the best. That's why we shown you also a picture as a 3D slice through this reservoir. You also see on a 3D slice predicted this outline of the reservoir, the blue one, the same as a red outline on a map from NPD. Yeah, exactly this outline. Yeah, this reservoir, and that's prediction by blue color on the 3D. If you on the map, if you can show in the bottom. It's this is the reservoir in the center, and also the 2D line going through this reservoir. So it's a properly called reservoir by. Yeah. So you can switch to the third task because I believe audience is getting tired, but we have still 100 very stable learners. It's nice to see.
You guys are great. It's like almost 2.5 hours we are going and discussing Python and Geo. And yeah, if we have so many people involved, it's really cool. So the third task will be quite short. Yeah, because we showed you mostly like now on 2D plots, how our results look like. And yeah, mostly, of course, it's interesting to have it in 3D. There's a lot of different packages existing for Python to plot your data in 3D, and you can just Google it, and you will be able to choose one you like. We will simplify it a bit. We will show you slice in different directions. So we now were showing slice in where is y-axis is time, but we will now show slice perpendicular to time. For this one, we will just read our libraries, read our data, and create extra column because this 3D data didn't have a column of impedance. And we will read one of our model which we created on the second step. So it's just a k-fold model for logistic regression. And since in previous step we used only 4 columns, we will use exactly the same features. Otherwise, we cannot use this algorithm. So, and when we will check our data on these features, yeah, you will see it's should come up. So we have 4 columns, and we have actually a lot of rows. It's so many rows only because we actually flattened our data. Normally data, like we have also all traces on top of each other. And in reality, you will have like some subset of this data. It's like first trace, some subset, it's second trace, because it's actually it's actually 3D even. So it's very big data. And when you normally given a SIG-Y 3D data, you will spend some time to reformat your data in a practical way that Python data frame can work with it. And yeah, it's most handy to actually have exactly the same format as your training data set. You only need to keep some indicator to rebuild 3D picture later on. So for example, you can keep indicator as extra columns as inline, X line, and so on. So I can maybe show you data, how it looked like. Yeah, it's actually, in reality, our data is written in this way that it has a column as an inline X line that we can plot it in 3D. So we starting like we know our data, we know our model which we will apply. So we will start prediction, and we will try to visualize it. So when we run prediction, we will see that there is still quite unbalanced data for predicting oil, but it's okay. It shouldn't be like, it shouldn't be 50-50, since yeah, you would never expect to have 50% of your 3D volume to full with oil. In some cases, probably if you have specific selection of 3D. And then we are going to only plot slice of 3D volume in perpendicular direction. So on this graph below, you can see that we actually, as a X using inline, and Y it's our X line direction, and it's perpendicular to all previous pictures which we had in exercise 1 and 2. And it corresponds to the picture which Vita showed in her presentation. And we only selecting some small thin line of specific time. So in line number 8, you can specify which timeline. We are taking the middle of the reservoir plus a few points up and few points down to, yeah, just not to miss if in specific time there was no reservoir detected. And we will group it by X line and in line to be able to plot it in 2D. So here, yeah, you see some visualization. It gives you an idea how it looks like. You can even plot it in 3D. It's very time consuming, but it's possible to run on your computer. And however, it's maybe easier to use some other more advanced program to plot in 3D, since you actually have now column of indicator 1 or 0 in your data frame, and you probably can easily export this data in some other programs. So I think we are finished with our exercise. Shall we go to questions? If there's some questions left over. Oh, I see Vita is answering question in chat.
Yeah, I'm trying, but I apologize if I miss some question, because it's a lot to navigate between different screens. So if I really miss it, I'm really sorry, but you can always write later if you still need answer, for example, to LinkedIn, and we will try to answer. But I think if you spend some time personally and just go through exercises, then it will be more clear what we've done and which part it works better. And for sure, you can modify it and bring more advanced solution. This is just an overview for you.
Yeah, so in general, this exercise is just learning point for you guys, just to see how, in which direction you have to work.
Sorry, inline, crossline, this is just map overview. It's a time slice through formation, and we are predicting within this formation where the oil and where the gas located. So that's what you see. You see 0, 1, where 1 is the blue dot that indicates hydrocarbons. So we can't distinguish if it's oil or gas. You can extend this code to make saturation, even predict saturation, not just 0, 1. But that's what you see. It's reservoir, outline reservoir. This is in the center of your arc full reservoir, a bit full. That's a marl reservoir. So you code it properly from the seismic.
Yeah, so in general, if you want to predict more like gas oil, you can use a multi-classifier, which will work with multiple parameters, like not only 0, 1, but it have 1 to 3 and so on.
If no more questions, I think everyone should go and rest now. It was quite intense. It's a lot of information.
So in general, yeah, it's Vita already emphasized in the chat that we used ML because it was not possible to use any alternative because we need to predict fluid from post-stack.
Yes, thank you very much. Really great and dense presentation, effectively. My question may be relatively simple. I wanted to know, because I'm studying a lot of reservoir geology in carbonate rocks, if with the particularities of carbonate rocks, we can apply the same settings, for example, that we saw here to have results that can be of use. Because in carbonate rocks, we have a lot of problem with diagenetic transformations and things like that. Do you think that machine learning can help us to distinguish what we can have as useful information to decide what to do?
I think you can use all the same techniques and the methods, but you have to learn from the carbonates. You have to bring new wells, formation with the carbonates, particular features, define maybe additional curves to learn from, have a look at your seismic, and then go ahead with the similar code with similar procedures. But that what we showed you, we learned for the sandstones. So okay. It should be different models for sure.
No problem. So I have to take in account the heterogeneities really well to be able to apply what we shown us today. Thank you.
Thank you.
No, I'm looking forward to the challenge of working through these examples. They're very intense, and it's incredible that you've given us all this data and the outline of the procedures to work with. A lot of investigation to do, but it's really wonderful to have this data and these, excuse me, and these notebooks as starting points. Thank you very, very much.
Well, I hope you will enjoy to work with that. Thank you for your interest.
Yeah, I look forward to getting to the point where I can show you something that you didn't produce yet. That would be nice.
We are sure that it can be done a better way, but we also please know that we are sharing the basics which we are allowed to share, because some of the project, it's commercial based, so the company invest in it, and a bit advanced features we didn't show here, and it's set for the one kind of level for EEG conference if it's accepted, and the second, of course, for those who paid. But still, for learning community, we try to collect the codes and give away the data so you can progress to the better way and give better solution to the world. So yes.
Well, even if I get to the point where I have a reasonable understanding of what you did, that would be pretty great for me.
But we can share also our abstracts, what we presented recently, and yeah, and I hope that EEG will be accepted. Then we can also share that, because there we in details specify tasks. Yeah,
that'd be great. Thanks.
Thank you.
Yeah. Thank you very much for this presentation. It was a very, very intensive one, I must confess. Having these data sets for practice and the guide that we've gotten from you all through the presentation would also help us run through this presentation, run through these notebooks with a bit of understanding. And if you have any other questions, we believe we can push to the organizers who will going to push them to you. So two questions. Although I mentioned one earlier during the break about how you were able to merge or do a seismic to well tie. I think I figured out that part of it. And then the other question is, how do we apply or how do we deploy these algorithms in structurally complex geology in areas where we have a lot of thrusting or folds or transcurrent faulting? How do we deploy this technology? How does it account for the reservoirs that we're trying to predict?
So the first question about well tie.
Yes.
When we just start to dig into this problem, we actually tie the wells and have a look at that. And Elena was showing you in the first exercise that she was using time. Remember time depths?
Right.
But then we find out that it was not really working. We have to take into account some kind of compaction trends. I was mentioning to that. And then we find that it could be simpler solution, that we are not going for this complex compaction trend, because one can design it like this, another one can design it a bit differently. We just go for formations. In this case, we don't really need to tie your well. You just check shot correlate your well. So you take time and the value. Instead of depth, you're taking the time. And then you learn from the well between the top formation and base of formation. So within the zone for particular formation, and you take it at each wells. So you learn, you make your model on that. And then you go to the seismic, and seismic you should interpret. You should put your horizons. And then you say, okay, my formation start here on the seismic and finish there on the seismic. And you again cut your seismic and make recognition only between these horizons. That saves you time, and that saves you to break your head. How can I address this problem with the compactions trend? We tried differently, but that was working. That was presented to you today.
Right. Yeah. So thank you very much.
You're welcome. Oh, it's such as great comments in YouTube. Thank you very much, guys. It was a lot of work for us. It was nearly 1 year, and that's what we presented to you. So it's our result. And I want to say that it was 3 companies involved with, and for example, Geo, they did great preparation for the logs petrophysics. It's really important how we data prepared, and it's all under AGGS, who is earning the data for all this merge. And PSSG, we did the merge, we did the inversion, and we work with this ML fluid prediction, where Elena is leading the Python code. So thank you very much. It's really nice to hear after all the time what we spent working this project to see great response. Thank you.
Right. I believe we have all learned something. We have all picked up one together. Okay. Yeah, I believe you can see me now. So I believe we have all learned something. We picked up one information or the other from what we have learned so far. And I also believe we would go back and practice with the data sets that we have for practice. And going forward, we would learn to deploy these algorithms in our work. And then just like Vita mentioned in the beginning of this presentation, that if you find another way around these problems, you could send your results in, and then you'll be given a certificate for these results that you have. And you can also use that certificate as a proof that you actually have these solutions, and you can deploy them when you want in complex situations. So we say a big thank you to everyone out there, all over the world, from wherever you're listening. We appreciate your time, and we believe this will be a stepping stone into your journey into the GeoPython world. Thank you very much.